Hey, this is Presh Talwalkar. This puzzle has been shared with the claim that only a genius could solve it. It has gone viral on Facebook and the internet, generating millions of views as people have debated what the correct answer should be. In this video, I'm going to present what many people believe to be the correct answer. Can you figure it out? Give it a try before watching the rest of the video. So most people believe the correct answer is 36. This is found by taking the product of the sum of the digits in each multiplication. When multiplying two numbers AA and AA, you obtain the answer by taking the sum of the digits in each multiplication and then multiplying that together. For example, to do 11 times 11, we would take the quantity 1 plus 1 and multiply it by the quantity 1 plus 1. This equals 2 times 2, which gets to 4 as given in the puzzle. Similarly, 22 times 22, the answer can be found by taking 2 plus 2 times the quantity 2 plus 2. This equals 4 times 4, which equals 16 as given in the puzzle. This would mean 33 times 33 would equal 3 plus 3 times the quantity 3 plus 3. This equals 6 times 6, which is 36. So most people believe this is the correct answer. However, there are people who think the answer should be 18. They believe the procedure to get the answer is to take the sum of the digits in the product of the regular multiplication. For example, 11 times 11 is equal to 121. The answer can be obtained by taking 1 plus 2 plus 1, which is 4. Similarly, 22 times 22 is equal to 484. The answer can be found by taking the sum of the digits in the product, which is 4 plus 8 plus 4, which is 16. This would mean 33 times 33 is equal to 1089. The answer can be found by taking the sum of the digits 1, 0, 8, and 9, which gets to the answer of 18. So we have two different answers. We have 36 and 18, and both methods seem valid. So is there any way to reconcile these two different approaches to the problem? In fact, there is a way to justify the answer of 36 under the sum of the digits in the product. Let's see how that works. So we start out with 11 times 11. We can expand each term in the multiplication to write this as 10 plus 1 times 10 plus 1. If we expand out this product, we get 1 times 100 plus 2 times 10 plus 1 times 1. This gets us to the familiar answer of 121. And if we take the sum of the digits, we get 1 plus 2 plus 1, which is 4. There's an alternate way that we could visualize what's going on here. We could do this by multiplying by lines. Let's do 11 times 11. For the first number 11, we'll draw one line, and then we'll leave some space and we'll draw another line. For the other 11, we'll draw lines in the other direction, leaving spaces between the two ones. We can now get to the answer by counting the number of vertically aligned intersections. On the far right, we have one intersection. This will be 1. In the center, we have 2 intersections. This will be 2. Finally, on the far left, we have one intersection, which makes for 1. So we can copy these numbers, and we get to our familiar answer of 121. Now we can add up the digits in the answer to get 1 plus 2 plus 1, which equals 4. So there's another interpretation that we've just shown is valid when we're summing up the digits of the product. What we're really doing is we're counting the number of dots in this diagram. So here we have exactly 4 dots in our diagram, and that corresponds to adding up 1 plus 2 plus 1. So let's continue this pattern. So we'll start out algebraically with 22 times 22. We can rewrite this as 20 plus 2 times 20 plus 2. We can expand this out to get 4 times 100 plus 8 times 10 plus 4 times 1. This is equal to our answer of 484, and the sum of the digits is equal to 16. So now let's look at the same problem visually. We'll do 22 times 22 by multiplying by lines. So for the first 22, we draw 2 lines for the 20. We'll leave some space and draw 2 lines for the 2. For the other number, we do the same thing, but draw lines in the other direction. We'll now get to the answer by counting the number of intersections that are vertically aligned. So we'll start with the group of intersections on the far right. There are 4 intersections here. In the center, we have one group of 4 and another group of 4. This makes for a total of 8 intersections. On the far left, we have 4 intersections. So copying these numbers, we get to our familiar answer of 484. And if we add up the digits in our answer, 4 plus 8 plus 4, we get 16, which once again is the number of dots in our diagram. So now let's apply the procedure to 33 times 33. We'll first consider an algebraic procedure. We have 30 plus 3 times 30 plus 3. We'll expand this out. We get 9 times 100 plus 18 times 10 plus 9 times 1. So we could write our answer as 9 hundreds, 18 tens, and 9 ones. And if we were to add up the digits in this product, we would get 9 plus 18 plus 9, which is 36. So this is not how we would typically write this answer. If you put 33 times 33 in a calculator, you would not get 9, 18, and 9. Although this is a valid representation of 33 times 33. What we do is in the decimal system, we never have any value be more than 9 in our placeholders. So the problem is this 18 times 10. We need to split that up into 10 times 10 plus 8 times 10. Now 10 times 10 is equal to 100. So that adds one more into our hundreds place. So we have 10 hundreds plus 8 tens and then 9 ones. Now 10 hundreds is also equal to 1,000. So our final answer is 1 times 1,000 plus 0 hundreds plus 8 tens plus 9 ones. So this is the more familiar way that we would write out 33 times 33, which is 1,089. But if we were to ignore this carryover rule, you could see this representation is a valid way to represent 33 times 33. And if we did add up the sum of the digits in this product, we would get to the answer of 36. One more way to illustrate this is by doing the visual multiplication. So we'll draw 3 lines for the 30. We'll leave some space and draw 3 more lines for the units 3. For the other number, we draw the lines in the other direction, again leaving some space between the tens and the ones values. So on the far right, we count the number of intersections. We have 9 intersections here. In the center, we have 2 groups of 9. This makes for a total of 18 intersections, and on the far left, we have 9 intersections. So we have our answer of 9, 18, 9, and we know this represents 9 times 100 plus 18 times 10 plus 9 times 1. We could go ahead and do the carryover process, and we would get to the answer of 1,089. However, if we just want to count the number of dots in this diagram, we would get to the answer that there are 9 plus 18 plus 9, which is 36 dots in this diagram. So that could be a valid way of counting the sum of the digits in the product if we don't take carryover and we just count the number of dots in each column. So what this means is we'll go over our procedure. So if we count the sum of the digits in the product, for 11 times 11 and 22 times 22, we do get 4 and 16 as in the puzzle. And finally, we then need to figure out what 33 times 33 is. We could validly write this as 9, 18, and 9 as long as we don't have any carryover and we understand where the placeholders represent. So this would get us to an answer of 36. And this would exactly match the procedure that we use to get the product of the sum of the digits. If you go through a plus a times a plus a, that's exactly what we're doing when we're doing the sum of the digits in the product with no carryover, and it's the same procedure that we're using to count the number of the dots in our diagram for visual multiplication. So it would seem that 36 is the answer to this puzzle. Did you get to 36?